My dear lovely viewers, welcome back to my channel. Today's another beautiful day and we have yet another exciting problem to tackle. So let's go see the problem and go through the solution as usual. So here we have the square root of 1 plus s power log 3 plus 3 power log x plus s power log 9, everything equal to 27 power log x minus 23. So this problem is very unique and uncommon. But what we shall do is to employ some intricate laws of logarithm, to solving it. The first we shall look at is a particular law of logarithm which is not in most mathematical tests, and I find it very bizarre. So we have this theorem: a power log b is actually the same thing as b power log a. This theorem is only valid when either a or b is equal to the base of this logarithm. Now, our problem we are going to solve, this problem we are going to solve rather, the base of all the logs we have here is actually 10. It's also called common logarithm, and sometimes it's intentionally omitted. So with this fundamental theorem, I can now say s power log 3 is equal to 3 power log x. So a power log b is equal to b power log a. So s raised to the log of the argument 3 is equal to 3 raised to the log of the argument x. And I shall call this k. Okay, having established that, we are then going to simplify s to the log to base 10 of the argument 9. I will now say, okay, s power log 9, and 9 is 3 squared. S power log 3 squared. So since the argument is raised to an exponent, the exponent will come to the back of the logarithm. This is going to be s2 log of 3. So if I use the power rule of exponent, I can write this to be s power log 3 all squared. No harm, no foul. When a power is raised to another power, we multiply the powers together. So 2 multiplied log 3 is 2 log 3. So I am going to say this is equal to k squared. Then on the right hand side, I have 27 power log x. So I can then say 27 power log x. 27 is actually a perfect cube. That is 3 cube. It will be 3 cube, then log x. As you can see, 3 is a power, log of the argument x is a power. I can also write this to be 3 power log x all cube. So since 3 power log x is equal to s power log 3, which is equal to k, I can then call this k cube. So having refined the radicands, I can then actually put them in the radical sign, which is the square root. So it implies that from what we have done, I will now take 1, then you look here that, okay, s power log 3 is equal to 3 power log x, which is equal to k. So for s power log 3, I write k. Then again, for 3 power log x, I also write k because they are the same from this theorem. Then s power log 9, that is k squared. So I'll write k squared here. Then on the right side, we have 27 power log x, which is k cube. I'll write k cube minus 23. So k plus k is 2k. So I'll write 1 plus 2k plus k squared. Okay? which is equal to k cubed minus 23. Then, okay, should have written k squared first. This is a quadratic expression. So this is actually the same thing as the square root of k squared plus 2k plus 1 equal to k cubed minus 23. Okay? Now, if you look at k squared plus 2k plus 1, this is analogous to something we know. Okay? We know that a squared plus 2ab plus b squared equal to a plus b all squared. Okay? Okay? A squared 2ab b squared. So if our a is k, then our b will be 1. That will be k plus 1 all squared. Okay? That makes sense. So if you compare this with this, we can then write that the square root of k plus 1 all squared equal to k cubed minus 23. So we are going to have a polynomial. So the square root here, we undo the squared. We are going to be left with k plus 1 equal to k cubed minus 23. Okay? I think this makes sense. Then, if I arrange this polynomial in its natural order, I will then be having k cubed minus 23 minus k minus 1 equal to 0. What I've just done here is to turn this equation. If a is equal to b, it implies that b is equal to a. Okay, if I rearrange this, it becomes a k cubed minus k minus 24 equal to 0. Okay, all right, we have done well. It's a depressed cubic equation. So I shall factorize it because of the k cube here. Then we move on. Okay, because of the k cube here, I will find a way to split 27. Okay, no, to split 24 so that I can get 27. I think that will help. So I can write k cube minus k minus 27, okay, plus 3 equal to 0. So you can see that negative 27 plus 3 is equal to negative 24. The reason why I'm doing this is because 27 is a perfect cube. I can actually match it with a k cube. So I would then write k cube minus 27 minus k plus 3, everything equal to 0. It's very interesting. Then 27 is a perfect cube, which is a 3 cube. Then I'll factor out 1 here. I'll be having k minus 3 equal to 0. Then I will then look for a formula for the difference of cubes. I know that a cube minus b cube can be factorized into a minus b. I will open another parenthesis. I will take a and square it. Take a and b and multiply it, which is ab. Take b and square it. Okay, so it means that k cube minus 3 cube, I can actually write it to be like this. So that would be k minus 3 in one parenthesis. Then I will take k and square it. Take k and 3 and multiply it. That will be 3k. Then take b, which is 3, and square it. That becomes 9. Then minus 1 into k minus 3, everything equal to 0. Okay, the spacer is quite tight. Please manage it. I think it's visible. So we can then see that k minus 3, k minus 3. So it means that we can pick the outside factors. It's okay. Now, for the sake of our audience, I can then try to write this to be k squared plus 3k plus 9 in one parenthesis, k minus 3, then I have negative 1, k minus 3 equal to 0. So as you can see, these two parentheses are the same. We can then pick their size factors. We'll be having k squared plus 3k plus 9 minus 1 in one parenthesis, then k minus 3 in another parenthesis, everything equal to 0. So 9 minus 1, that would be 8. So we have k squared plus 3k plus 8. Then we have k minus 3, everything equal to 0. So now we've actually gotten the 3 factors, 1 here and 2 in these quadratics. But we have to test whether these quadratics actually have a real root. Because according to the product power rule, we are going to say it implies that k squared plus 3k plus 8 equal to 0 or k minus 3 equal to 0. So we need to test using discriminant whether these quadratics will have a real root. So I'll take up this part. We are the last lab. It's a nice problem with a very beautiful solution. Okay, b squared minus 4ac. b squared minus 4ac. This is discriminant, of a quadratic equation. Here, a is 1, b is 3, and c is 8. Okay, 3 squared will be what? That will be 9 minus, 4 times 1 times 8. Okay, that will be 32. Okay, this is going to give a negative value. This is going to be negative 23. So it implies that this quadratics does not have a real root, but we can actually look for the roots in the spiritual or imaginary world. So we are going to reject this quadratics. So this is rejected. Then means that our only solution is k minus 3 equal to 0. So k is equal to 3. So this is the only valid solution for k. Now midway, we made a substitution. Okay, that's not even midway. At the very beginning, we said that k is actually equal to 3 power log x or s power log 3. So anyone we decide to use to give us the value of x. So if I use the first one, so 3 power log x equal to 3. So, and 3 is something as 3 to the power of 1. So because the bases are the same, they can cancel out. The exponents are equal. I will then write log s equal to 1. Mind you, I said that if the base of a logarithm is not written, that log is in base 10, then I can then write log to the base of 10 of the argument x equal to 1. So if I then transform this logarithmic equation into an exponential equation, I'll then be having x equal to 10 to the power of 1, which is equal to 10. So this is the value for x. Thanks, viewers. Please give this video a thumbs up, share with your learning friends and colleagues, and don't forget to subscribe and turn on the post notification so that you wouldn't miss out in our next video. See you and God bless.